Okay, now let us, as an application rather, generalize our previous example to n dimensions so that we have such an example as well. So the problem is the following. Okay, let x1, x2, xn be non-negative numbers such that, okay, their sum is A. Well, A is some positive number. Okay. So question is, find maximum of the function of the product. Now, this may look a little bit complicated, but it's not at all. It's exactly the same idea. Of course, here we assume, we know, that Lagrange method works here. Well, it does, of course, because these are differentiable functions, and so on. Okay, the idea is to use this to obtain something, a serious result in mathematics, an inequality. Well, this is, of course, a Lagrange problem. Namely, we want to find the maximum value of this product, okay, subject to the condition that their sum is A. Okay, so, okay, we have gradient f plus lambda gradient h equal to okay, this is an n-fold matrix. And of course, h must be 0. That is, the sum must be A. Now, let us see what this first condition tells us. Okay, this, of course, means the following. Okay, gradient f here means f sub x1, f sub x2, and so on, up to f sub xn. Well, because of the product, this, of course, means that x2, x3, up to xn, that's derivative with respect to x1. All the others are constant, plus lambda, derivative of h, that is this function, is certainly 1. So this will be 0. Similarly, for the second one, x2 is the variable. So we have x1 times x3 up to xn plus lambda times 1 is 0. And this continues like this. And at the end, when we differentiate with respect to xn, we have x1, x2 up to xn minus 1 plus lambda times 1 is 0. Now, of these equations, the idea is to subtract one from the other. Okay, but before that, let us observe that if any of xi is 0, then the function becomes 0 at that point. So, or let me say, the product is 0. And because these are non-negative numbers, okay, this is the minimum. Okay. We are not interested in this. So let us, let me give names to them, 1, 2, etc. So we consider 1 minus 2. Okay. It says that lambdas cancel out, and we have all the factors the same, x3 up to xn, times x1 minus x2 equal to 0. Okay. Here, of course, I mean, so xi's are positive. Okay, let me say, so assume xi is positive for every x. Well then, if they are positive, you can cancel them. So this says x1 must be equal to x2. Well, similarly, if you subtract any one from the other one, you get equality of all of them. So, similarly, okay, one gets x1 equal to x2 equal to xn. Well, this says that xi, or rather, okay, because they are all equal to each other, we have x1 plus x1 plus x1 equal to a. Okay, this is n many. So x1 is equal to a over n. Okay. But then, because they are equal, this is x2, this is x3, it's xn. Now, what this says, okay, is the following. Well, obviously, so the point P0, a over n, a over n, a over n, okay, is a critical point. Well, because the sum is a, okay, these values are all bounded by a from above, and so, because of continuity, it has a maximum anyway. It cannot go to infinity. Okay, so this gives the maximum. Well, this means the following. Hence, f of x1, x2, xn, which happens to be the product, is smaller than the maximum value, well, which is f of a over n, a over n. Which, on the other hand, is a to the n divided by n to the n. Okay. Now, in this inequality, take nth roots. Well, one gets the following. This is bounded by a over n. But a was the sum. Okay. Now, this is proof of the fact that the so-called geometric mean is always smaller than the arithmetic mean. So we proved this inequality. Okay. It's a well-known inequality. One can prove it using much less machinery in mathematics, namely more easily. Okay, but this is also not a difficult calculation. Well, our next example will be considering problems of extrema. That's to say, we want to minimize or maximize some geometric thing or some quantity, and we have some restrictions. How can we achieve that? So it's a purely Lagrange problem. Well, let me say problems on extremes. I will consider two problems here. Okay. One of them is the geometric problem. Okay. A rectangular box with sides, okay, parallel to coordinate axes is put in the tetrahedron, but it's better known as a pyramid, okay, with vertices at the following points, namely 0, 0, 1, 0, 2, 0, 1, 0, 0, and 0, 0, 0. Question is, find the dimensions such that its volume is largest. Okay. As with problems of extrema, optimization, that is, in one variable as well, okay, we usually sketch so that we can see better what the geometry really says. Well, first of all, we have a pyramid with these vertices, so it is something like this. Okay. On the x-axis, okay, that is this one, we have 1. On the y-axis, we have 2. On the z-axis, we have 1. And we have the origin. So these are the 4 points, okay, describing the pyramid or the tetrahedron. So it is like this. So this is our pyramid. This is the height, and this is the base. Now, we are putting now we are putting a rectangular box inside this pyramid so that the sides are parallel to the coordinate planes. Well, of course, if you just put your box, a little box somewhere here, you can extend it until its sides touch the coordinate planes. So it's easy to convince yourselves that such a pyramid must have the following picture. Okay. Up to some point, well, they must be parallel, of course, and this is parallel, and so on. Okay. Now, what happens, of course, is that in this rectangular box, we don't see these points, they're all inside. At some point, its diagonally opposite corner to the origin, okay, must touch, okay, this plane. Okay. So this point is extremely important for us. So this point, let us call it x, y, z, okay, will be on the plane. Okay. Determined by, of course, these 3 points. Well, I write 1, but to emphasize just this distance, but the others, y and z, are, of course, zeros. Okay. Well, what is the equation of this plane? So this plane is passing through, okay, the points 0, 0, 1, okay, 0, 2, 0, and 1, 0, 0. Namely, it's the plane at the top passing through these 3 points. We can find its equation. Well, you can, of course, find it by calculating P1, P2, and then P1, P3, taking the cross product for the normal, and put one of the points as we did at the very beginning of our discussions with planes, but you can do it more practically now. Okay, namely, you have x, y, and z, okay, and at, for example, y0, z0, and x1, you want to get 1 at this time. So this would be, okay, x plus 2y, rather 1 over 2, and 1z, that would be 1. So trivially, this satisfies all these points. Namely, if you put 0, 0, z is 1. If you put 0, 0, y is 2. And if you put 1, 0, 0, okay, you get the rest. It passes through all these points. Well, so in the Lagrange sense, what does this problem say? It says the following. Okay? We want the volume to be maximum. That means the product should be maximum. So the question is, okay, maximize, okay, f of x, y, z, the volume. Obviously, the volume of the box is x, y, z because the sides are directly x, y, and z. Okay. And what is the restriction? The restriction is that x plus y over 2 plus z is 1. Well, this is not enough, as we did before. Okay. Here we don't have just this. We also have that x, y, z are non-negative. Now, under this condition, under these conditions, rather, when x, y, z are non-negative, we are going to satisfy this equation. Of course, it says that all x, y, z are bounded. We are talking about a closed and bounded set. And this function is a polynomial in 3 variables, so it's continuous. So maximum and minimum exist. Okay. Obviously, if 1 of x, y, z is equal to 0, then, okay, volume is 0, and this is the minimum. That means on the coordinate planes, on the zx, zy, or xy planes, if you take any point from those surface triangles, the volume will be 0, because one of the coordinates will be 0. So assume these are all positive. Well, under this condition then, Lagrange tells us that gradient of f, that would be yz, xz, and xy, okay? And gradient h, here h is, of course, this term, -1, but that doesn't play any role. It's just 1, 1/2, and 1. So, okay, yz plus lambda 1 will be 0. Xz plus lambda 1/2 will be 0. And xy plus lambda will be 0. Okay, so these are coming from the parallelity of the gradient vectors. And of course, we have this to satisfy. So we have 4 equations. And of course, 4 unknowns. Okay. Now, pretty easily, okay, we can check 1 minus 2, which gives, of course, 1 minus 3 first, which gives, of course, lambdas cancel out. So we have y times z minus x, which says that y is 0, but this is a contradiction because we assume they are all strictly positive. So it says z is equal to x. Well, once z is equal to x, we can check now the second one, namely, now consider 2 times 1 minus, say, 3. Oh, sorry. What happens? 2 times 2 minus 3. Because if you multiply this by 2, lambdas will cancel out when you subtract 3 from it. So we have then 2xz, okay, plus lambda is 0. And we will subtract from it 3, which is xy plus lambda. So subtracting, we get x 2z minus y is 0. So either x is 0, but x not 0. This is a contradiction. So 2z is y. Okay. Now we have z is x and 2z is y. So put in 4, namely, okay, we have x plus y is 2z. Maybe we should change them to z's. Okay, x is z plus y is 2z. So this is 1/2 times 2z plus z. Okay, this is y equal to 1. So this says that z is 1/3. Well then, okay, y is 2z, so it is 2/3, and x is z, so it is 1/3. So our point is 1/3, 2/3, and 1/3. Okay. Well, because we have only one critical point, and there is a maximum, this gives maximum, which is the product, so it is 2/27. So the volume is this, and because we know the point, we know the dimensions directly. Okay. Well, let us now consider a more tedious calculation. That's to say, as a second problem, okay, a rectangular box is to be manufactured, okay, such that okay, the materials that will be used for the bottom, for the top, and for the sides will be different, such that the materials used cost, okay, A, of course, this is per unit square. Okay. For B, let me be, okay, XY, so for the bottom. And it is B, again, per unit square for the sides. And it costs C for the top. Of course, here we assume that A, B, C are all positive. Okay. Of course, I mean, if you say this much, it is not restrictive. We want this box to have a volume of V0. If this box, okay, is to have a volume V0, of course it's a positive number, okay, find the dimensions so that cost is minimum. So from the wording, we understand that we have to calculate the cost and minimize it, subject to the restriction that the volume is V0. So suppose, okay, the dimensions are the following. Okay, it's a rectangular box. Okay, this is X, this is Y, and say this is Z. Then, of course, the cost will be clearly the bottom. Well, the cost was A for the bottom. And the sides, well, the sides are XZ or XY, and you have two of them each. And the cost is B. And finally, the top, well, the top is the same as XY, and you have C there. You have 6 sides. So this is the cost function. We want to minimize this, okay? Subject to the volume is V0. Now, well, it's a clear-cut Lagrange problem. Okay, we can say HXYZ is XYZ minus V0. And you can call this f of XYZ. Okay. So we have one condition, and we have a 3-variable function. So we will have a system of 4 equations to solve. So we calculate gradient f. Well, gradient f would be derivative with respect to x. So ya plus 2z, 2z plus yb and yc. Actually, we have here xy times a plus c. Anyway, so this is the derivative with respect to x. With respect to y, we have xa for the first one. And for the second one, we have 2bxy, so that would be 2bx. And for the last one, we will have x. Something is wrong here. Yes, of course, it is wrong. The sides are either xz or yz. So this should be yz. Okay. Top and bottom are just xy's. So let me correct that. We have here ya, right, and here 2zb. So this is just 2zb with respect to x, and yc. Fine. Now we have, with respect to y, xa times 2zb here, and the last one, dx. With respect to z, we just have 2x plus yb. So these are the derivatives for f. Well, for gradient h, we have, as before, yz, xz, and xy. Okay. So, adding them with the Lagrange multiplier, we end up with the first term. So, it's a plus, I should write them, well, let me write them like this. A plus c y plus 2zb plus lambda yz is 0. The middle term, it is c plus a again, x plus 2zb. Okay. All right. And lambda xz, that is 0. And finally, the last term, 2x plus y b plus lambda xy is 0. And finally, that xyz is 0. Okay. Well, we want to solve this system. Of course, for things to cancel each other, okay, here we have y, here x, we have to equate them somehow. That means we have to multiply this with x, this with y. And for this, as I already remarked before, not to lose information, we want to guarantee that x, y, and z are non-zero. Well, obviously they are non-zero because the fourth equation tells us none of them can be 0, because the condition will not be satisfied in that case. Okay, so firstly, by 4, x, y, z are strictly positive. And, okay, call these 1, 2, and 3. Okay. Now multiply, okay, 1 by x, 2 by y, okay, and we can, well, that much is enough for the time being, and obtain the following. If you multiply this with x, you end up with a plus c xy plus 2zbx plus lambda xyz. Okay, that's 0. Okay, from 1. From 2, we have a plus c, okay, multiplying by y. This would be xy plus 2z dy plus lambda multiplying by y, xyz equal to 0. Okay. Now, of course, subtract. When you subtract, these cancel out. The last ones cancel out. You have 2bz x minus y is 0. Okay. Now, starting from here, well, since z is not 0, okay, they are strictly positive, by the way, we get x equals to 1. Okay. Well, so this is the basic starting point. Okay. So here we got x equal to y. Now let us get a similar thing, okay, from the second and the third equations. Of course, if we multiply this by z, okay, these terms would cancel out. And this by y, of course. So this would simplify things a little bit. Let us do it. Now, similarly, multiply, okay, say 2 by, let me see, 2 was this one, so we multiply it by y, okay, and 3 by z. Now, we would obtain, in this case, well, why I'm doing it is I want to eliminate lambdas. To eliminate lambdas, on the right side, I have to have the same product, x, y, z. So I'm trying to get that go. We already used 1 and 2. Now we are using 2 and 3. Okay, so 2 gives us a plus c, okay, and that's 2. Right, we multiply it by y, so it is xy plus, we already did this actually, 2byz plus lambda xyz is 0, and 3 gives us 2x plus y, and we are in 3. Okay, we have a b. We multiply it with z, and plus lambda xyz equal to 0. Okay. Now, subtraction yields, okay, I have a plus cxy plus 2byz. These will cancel out, minus, okay, 2x plus y bz, and that's all. This is it. Because these terms cancel out, and that is what I intended to do. Well, if you simplify these things, of course, a little bit, you have here 2ybz with a minus sign, and you have this. This cancels with this one. Okay. And this, of course, what remains is the following. In what remains, let me rewrite it. This is xy minus 2xbz is 0. We can cancel x's because x is not 0. Okay. So that says z is a plus c over 2b of y. Now, this information is sufficient for us because we already know that in these calculations, okay, x is y. So put in 4. That means, okay, we have x, we have y, we have z. Equal to v0. Now this says y can be calculated. It's the cube root of 2b over a plus c v0. The cube root. Well, x is y, so it's the same. Z is a plus c over 2b y. Okay. So it says, you can simplify a little bit if you want. If you don't want, that's it. Okay. Obviously, the product, okay, this would be 2/3, and this would be, let me see, x and y are the same, so you have 2/3 of that. So this would be 2b over a plus c v0, and of course these will cancel out. You will get v0 at the end, and this certainly gives maximum. So the point is then this. That is, it is 2b over a plus c v0 and the cube root. The second one is the same. And the cube root. And the last one is, that should be a plus c over 2b to the 2/3 times v0 cube. Okay. So this would indeed give us what we wanted. Right. Now, let us consider a different type of example. Actually, this was our starting point in all these discussions. That was, well, okay. So this is my sixth problem. Okay, find the absolute maximum minimum of the function x squared plus y squared minus 2x minus 4y plus 6 on the set of xy's so that x squared plus y squared is less than or equal to none. The closed unit circle, disk, okay, with radius 3, centered at the origin. Now, firstly, okay, this is not a purely Lagrange problem. Why? Because we are not on the boundary only. Okay, we have the inside of the disk. Okay, should be considered as well. Okay, so now let us recall our starting point when we discussed Lagrange, namely what we had. Well, firstly, we have a differentiable nice function, and the domain is closed and bounded. So, since f is differentiable, actually continuity is enough, hence continuous, and D is a closed disk, so it is closed and bounded. Okay. F has minimum, maximum on D. So they exist. Okay. The next question is, where do they exist? They can exist at an interior point or on the boundary. So, okay, in interior of D, that is without the boundary, okay, boundary circle, okay, this means that they will be among critical points. Let me say they would be critical points. Okay. So we directly check critical points. Okay. So, okay, we check gradient f 0, 0 for the critical points. Well, this very simply says that f sub x, that would be 2x minus 2. F sub y, that would be 2y minus 4 is 0. So we get a point which is 1 and 2. Okay. Now the next question, is this point inside D? Well, you take the squares and add them. You get 5. It's less than 9. So yes, okay, it is in D. We checked. Now, it may happen that this maximum and minimum can occur on the boundary. Now, on the boundary, of course, this is a Lagrange problem. So the question now is, okay, to maximize, okay, to find maximum minimum of f, okay, such that x squared plus y squared is math. Now, this is a Lagrange problem. on the boundary, however. The other one was in the interior. Okay? Then we have a free critical point, so the directional derivatives are 0 is enough. But here we want to find the maximum under this restriction, under this constraint. So this is a Lagrange problem. Okay, well, what does that say? We calculate gradient f plus lambda gradient h is 0, 0, which of course means in this case we already have f sub x over there. It's 2x minus 2 plus lambda. The gradient of h, well, that is obviously 2x. And the derivative with respect to y, 2y minus 4 plus lambda. Now, derivative with respect to y of h, that would be 2y, and that is 0. Okay. And also, we have x squared plus y squared is 9. So maybe I should not write that here. Let me say, and x squared y squared is 9. So we have to solve this system. Okay. Well, before we attempt a solution of this system, let me give names again. Say the enumeration. Obviously here we observe that, okay, if, for example, x is 0, then we get contradiction. 2, 1. Because 1 says if x is 0, minus 2 must be equal to 0. Similarly, if y is 0, minus 4 is equal to 0. And if y is 0, then we get contradiction 2. So xy are not zeros in the first place. Well, if they are not zeros, then we can manipulate 1 and 2 so that we can get rid of lambdas. Therefore, okay, multiply equation 1 by y, 2 by x, okay, and subtract. Okay, so what do we get? 2x minus 2 y plus 2 lambda xy minus, okay, 2y minus 4 multiplied by x, okay, and plus 2 lambda xy. Of course, these cancel out. Okay, and we have 2xy, and we have here minus 2xy. They cancel out, so we have minus 2y, okay, and plus 4x is 0. Of course, here, what did I do? I did nothing, actually. Just opened up parentheses and found this. This says that y is 2x. Well, from here, okay, we get our point. Well, we put them in the third equation. Okay? So we obtain x squared plus y squared equal to 9. So x would be, okay, that's 5, 9 over 5, under root plus minus. Okay. Right. So this gives us two new points. One of them is, okay, 3 over root 5 actually. Okay. Y is 2 times x, so it is 6 over root 5. And P2, which is the negative here, and the other one is 2 times x. So we have 3 points, P0, P1, and P2. Okay. Now these being the only possibilities, okay, we replace them in the equation. Let me see. Oh. Okay. Well, okay, let me not do the calculation. Directly copy from here. So f of P0, okay, would be 1. And f of P1, that is the positive one here, that would be approximately 1.8. There are roots in it, so I don't want to go into that. F of P2 would be okay, that would be 15 plus 10 times 3 over fifths. Okay. So it follows that indeed this gives maximum, okay, and this gives minimum. Note that this P0 came from a critical point. This P2 came from the boundary. So it can happen. Okay. Well, in summary, this is exactly what we did before. In one variable, we considered inside of the interval. That means we checked for critical points. And the endpoints, there were 2 of them. It was easy. Now here, the endpoints becomes the boundary curve. And so we had to use Lagrange multiplier method. Okay. Now, before I finish, let me give you an exercise. Okay. Find minimum maximum of f xy, which was x plus y, on, okay, the b, which is this one. Actually, I gave this at the very beginning of our discussion of Lagrange multipliers. It was something like this. Okay, these were 2's, these were 1's, and this curve was x cubed y plus xy cubed is 9. Right. Is that right? Let me see. If x were 2, okay, y would be 1. So that would be 10 actually. Okay. So this is D. We could, of course, check the critical points very easily. There are no critical points actually. The derivative of x of f with respect to x is 1, with respect to y is 0, so the gradient is never 0. That means, okay, there are no critical points. So the minimum and maximum must occur on the boundary. Of course, on these 3 pieces, or rather 4 pieces here, okay, the calculation is easy because here, or here, or here, or here, one of them is constant. You just consider the endpoints and the derivative. The derivatives are non-zero, and so you don't have any critical points. Just check the points on the corners. But for this part, okay, you have to use Lagrange method. So let this be an exercise. Okay.